either factor, or we can solve for cosine squared and then square root both sides. Your choice. I think I'm going to solve for cosine squared theta and square root both sides. Plus or minus the square root 1/2. I have to do plus or minus here. Okay, when you square root both sides, you have to do it. All right, so I'm going to rationalize that radical, and cleaning it up makes it positive or a negative root 2 over 2. Now, I recognize that on my unit circle. Here is positive root 2 over 2 for cosine value. Here is a negative. Here is a negative root 2 over 2. Here it's a positive root 2 over 2. So what angles are these? Well, there's technically a couple different four different angles, right? So I could write pi over 4 plus 2 pi k, pi 3 pi over 4 plus 2 pi k, 5 pi over 4 plus 2 pi k, and 7 pi over 4 plus 2 pi k. Now, here's what I will tell you. These two can be condensed into one. So you can write it as two separate ones. That's this one here and this one here. Since they're across from each other, though, I could say collectively pi over 4 plus 1 pi k, because it's a half cycle later. Okay, so they could be combined into a single one. Likewise, these two are half a cycle across from each other. So I could say 3/4 pi plus pi k, which is half a cycle later. Okay? All right. Now, specifically, they want the ones that are from 0 to 2 pi only. Well, this is only a theta. When theta gets messed with, we'll have to change our approach. But since that's just a theta in there, I can see that the answer is going to be, let's use the red. If I use the red, if k is 0, we get a theta of pi over 4. If k is 1, we'll get theta is 5/4 pi. Why? Because we're doing 1 pi later, plus pi over 4. Okay? If k is 2, we'll get 9/4 pi, and that's bigger than the region of interest that we want, so we don't need that. If I go k is negative, it'll be too small for this problem. Okay, now let's go down here and do it with this one. If k is 0, we get 3/4 pi. If k is 1, we get 7/4 pi. If k is 2, we get 11/4 pi, which is bigger than 2 pi, so we don't want it. If k is a -1, we'll get negative pi over 4. It certainly is a location, right? However, we only want the answers from 0 to 2 pi, so that one's too small. So the solutions are, for this region of interest, pi over 4, 5 pi over 4, 3 pi over 4, and 7 pi over 4. Okay? All right. This is interesting. They want the answers from 0 to 4 pi. 0 to 4 pi. Something to think about when we're plugging in our k values. All right, cosecant. Well, it might be easier if we rewrite this with sine instead. So instead of cosecant, we will go 1 over sine of theta equals -2. Now, this 2 is over 1. If I reciprocate the left side and I reciprocate the right side, now it's something I remember from a previous example. Where is the sine of theta equal to a -1/2? Here and here, right? They're not across from each other, so I need to write this 2 different ways. I can't combine them. So I would say this happens when theta is, let's see, what angles are these? 7/6 pi plus any full cycle later, and 11/6 pi plus any full cycle later. Okay? Now let's take these and we're going to plug in integer values for k. You should consider the negatives, even though most of the time it doesn't work. But it depends on what the angle, how they have this angle represented. Okay, the zeros are the easiest ones, right? 7/6 pi and 11/6 pi. If k is a -1, it's 7/6 pi minus 2 pi. Well, that is going to be, let's see, 12/6, -5/6 pi. That's too small because we want to stop at the 0 mark. The next one, if we have a negative k value, 11/6 pi minus 2 pi, this would be a -pi/6. I mean, it's on our picture, but it's smaller than our region of interest that they're asking for. All right, if k is a 1, we have 7/6 pi plus 1 full cycle, right? Because k is a 1, and you're going to put it here in the k spot. This would be a 12/6, add them, you'd get 19/6 pi. Let's do it again for this one. 11/6 pi plus 1 full cycle, which is 12/6. 11/23/6 pi. Okay. Now we want to go all the way up to 4 pi. So this is between 0 and 4 pi. This is between 0 and 4 pi. This one's between 0 and 4 pi. This is between 0 and 4 pi. But what if k was 2? So we would have 7/6 pi plus 4 pi. Well, I already can see that that's going to be greater than 4 pi. How about 11/6 pi plus, if k is a 2, 4 pi. I can already see that that one's bigger. So my solution, now sometimes depending upon your instructor, you want the solutions listed as a set of values. So theta is 7/6 pi, 11/6 pi, 19/6 pi, and 23/6 pi, like so. Now, if you are questioning those, you can plug them back into the original equation and check to make sure it equals -2. Okay. All right. What if we mess with the angle? That's what this next one is about. What happens when we mess with the angle? I need to now figure out where this is. It's not just theta now. There's more going on in there. When does tangent equal 1? Here and here. That means that this, all of this, has to equal pi over 4 or 5 pi over 4. Okay? So theta minus pi over 2 equals pi over 4. Now these are across from each other. So I can say plus pi k. Half cycle later. So here or here. Okay? I'm going to solve this for theta. Theta now equals, I'm going to add pi over 2 to the other side. There was already a positive pi over 4 there and a pi k. I can't add the k to the other stuff, right? But the two non-k numbers I can add together. We will have 3/4 pi plus pi k. It doesn't look like this should be the answer, but this is the answer for all solutions. Okay? Now, they don't want all, they want just the ones in our region of interest. So this is where we need to start thinking about what we could insert for k values and get values between 0 and 2 pi. Okay? So if k is 0, that's the easy one. We get 3/4 pi. If k is a -1, we would have 3/4 pi minus pi, and that's a -1/4. Well, that's below our region of interest. If k is a 1, we'll have 3/4 pi plus 1 pi. Right? I'm plugging in this k value into here to see what we get. We will get 7/4 pi. If k is a 2, we will get 3/4 pi plus 2 pi. Will this be bigger than 2 pi? Yes, it will. So the solutions are 3/4 pi and 7/4 pi. All right, moving on. This one looks very complicated. The +3 is not in the function with tangent. So it's like this is the closing of that tangent, okay? All right. I think I'll distribute this 2. And then I'm going to take steps to get this so tangent of x is by itself, okay? I have tangent of x equals -1, and that happens here and here, straight across from each other. So that happens when x is (3/4 pi plus pi k). This is all the solutions forever and ever. And if I want the specific ones in this region of interest, we plug in some k values. If k is 0, we will get 3/4 pi. If k is a 1, we will get 7/4 pi. If k is a 2, we will get 11/4 pi, and that's larger than 2 pi, so we don't need it. If k is a -1, we get -pi/4. That is too small, so we don't need it. So here are our two solutions. Okay. Solve the equation exactly. So when they say exactly, no calculator, we're not going to have any rounded numbers. Solve the equation exactly. To me, this is quadratic in nature, and it equals 0, so we should try to either factor or use the quadratic formula. Okay. I don't see this as being factorable, so quadratic formula. If you don't know what it is, you should pause and look it up. Variable is equal to opposite of b plus or minus the square root b squared minus 4ac all over 2a. So the cosine of theta is all right. I ran through this with a plus sign, and I got this. I ran through it with a minus sign, and I got a negative number. No, I didn't get a negative. What do I get? Grab our calculator. -3 minus root 13. And then I'm going to divide that by 2. -3.3. We know that the cosine function toggles the values of it that we get, toggles between -1 and +1. This is undefined. There's no solution there. But the top one does have a solution. When does this happen? When is the cosine value 0.3? When is basically, if you're looking at your unit circle, it's not going to be on there, but if you're looking there, you would be looking at when is x really small, positive and really small. It's going to happen up here in quadrant 1 and down here in quadrant 4. Okay? That's when x is really small. Well, our calculator will give us the first one if we do inverse. Inverse cosine, 0.302. Inverse cosine, 0.30. I think it was a 7 after that. And we get 1.263. 1.263. This angle is 1.263. Now, since cosine is even, I could say that this angle is a negative 1.263. Now, if you don't want that as a negative angle, we could add a full cycle to it. What is that? Plus one trip around, right? Plus one trip around would give me $5.0199. Okay? Now, I wanted all of the answers from 0 to 2 pi. I have this one, and I had this one which was negative, but I knew I needed to add one full cycle to it, which gave me this one. So my solution set is 1.263 and 5.01999. Could I write the generals? Sure. They're not asking for that, but if I was going to write the generals, I would say this plus a 2 pi k, this plus a 2 pi k, and those would be the two generals. All right, let's go again. This one, options. Is it factorable, or should I use the quadratic formula? This one I do see as factorable because I can say 2 sine theta and if they're both minus, I'll get a minus 2 sine theta minus 3 sine theta for the minus 5 sine theta in the middle, and I will have the plus 3 on the back end. So those are my two. Now this is equal to 0, and I solve them each. This one, sine theta is equal to a positive 3/2. Will sine theta ever equal a number greater than 1? There's no such angle for that. This one, sine theta is equal to a positive 1. That happens here. When theta is pi over 2 plus any full cycle later. Well, they want all, this would be all, and they are asking for just with one trip around. This would only be pi over 2 for an answer. Okay, let's go again. This is also factorable, or you could use quadratic formula. C value is 0. I see it as factorable because we could, one, it's equal to 0, which we like. We could take out the sine of theta. What's left inside would be a 2 sine theta plus 1. It's equal to 0. Set each piece equal to 0. So sine theta equals 0. 2 sine theta plus 1 equals 0. And you solve them each. This one, sine equals 0 here and here. When theta is 0 plus 2 pi k, or pi plus 2 pi k, or they can be combined into a pi plus pi k because it's every half cycle later. The next one, solving for sine would equal a negative 1/2. Well, when does that happen? That happens here and here. When theta is 7/6 pi plus every full cycle later, and we could say negative 1/6 pi plus every full cycle later. Okay, so these would be all. Now you could also say 11/6 for the bottom, right? That was just one cycle later. They want the specifics, so we're going to put in k values. When k is a 0, we will get 7/6 pi and a negative 1/6 pi. When k is a 1, we will get 19/6 pi and a 11/6 pi. When k is 2, this would be 4, 24, 31/6. That's way too big. When this one would be a negative 1/6 pi plus 24/6 pi. That's 23/6 pi. That's also too big. And this one is too small. And we're looking to go to 2 pi, so anything over 12 pi, that's too big. These are the only two answers. Okay? All right, I think you get the idea. I might, for the sake of time and the lengthiness of my video, stop for this part. Okay, let's look at this example 14 here. I am seeing kind of a lot going on with this example. This, though, looks familiar. Cosine times cosine plus sine times sine. I'm thinking that this is a sum and difference formula. So let me look at my formula sheet. Here's my sum and difference formulas that we've covered earlier. So sum and difference formula. We have a sine, cosine, and a cosine, sine. I believe that's what we had here. Nope, we have a cosine, cosine, sine, sine. So that's this one. Now, we'll talk about the plus and the minus, right? We have to reevaluate that. U and V, U and V. So this is a U, this is a V, this is a U, this is a V. There's a plus sign here. So when we condense this, if this is a plus sign here, that's on the bottom, that means that's a minus sign here. So this can be simplified to the cosine of U minus V, like so. Well, this is the cosine of negative 1x then. I happen to know, and so do you, that cosine is an even function, so I can rewrite this as just cosine x. So this is saying that cosine x is equal to root 3 over 2. I know. Why didn't they just say that, right? Okay, so what does this mean? Where is this happening? Well, cosine value that has a root 3 over 2 is going to happen here and here. That happens when the angle, they're using x for the angle now. That happens when the angle is pi over 6 and when the angle is a negative pi over 6. Now, any full cycle later for each one of these is a valid spot that will produce a cosine value of positive root 3 over 2. Okay, now some of you are probably thinking, I don't want that to be a negative. That's fine. Go all the way around and write 11 pi over 6 instead. That would be okay. All right. Now, to find all of the solutions, this is all forever and ever, right? So this is all forever. So if we want just the solutions from 0 to 2 pi, we're going to put in different k values. If k is a 0, I get pi over 6 and negative pi over 6. Well, this one is below my interval of interest, so I'm going to cross it off. If k is a 1, the top one becomes 13/6 pi. Well, that's too big. That's bigger than 2 pi. And the bottom one will become negative pi over 6 plus 2 pi, which is 12/6 pi, right? So we'll get our positive 11/6 pi there. If I continued going and I did k equals 2, I would find they would both be out of range. And if I did a negative 1, well, the bottom one would already be negative and the top one would become negative. So these are the only two solutions. 15 here is, we're going to solve it using double angle formula, which basically means, hey, you can't solve this the way it is with a 2 theta here and a theta here, right? If, if they were the same, then maybe we could talk about theta being any number, right? But that's not the case here. So we're going to use our double angle formula to rewrite cosine of 2 theta, okay? Which means we are going to use, let me point out the double angle formula we're going to use and refresh my memory right here. I'm going to use one of these. This one or this one, or this one. And I typically think of myself as a lazy mathematician, so I'm going to use this one. And the reason I'm thinking about using this one is because it'll give me a function that's quadratic, and then I can make the equation equal 0, and I can solve it using either the quadratic formula or factoring. So I'm going to make the cosine of 2 theta equal to 2 cosine of theta squared minus 1. Oh, my pen's not working. 2 cosine of theta squared minus 1, that's on the left, equals cosine of theta. If I make this equal 0, I'm going to subtract cosine of theta on both sides. I still have that minus 1 there. I sneakily made the order this way so that I could see it's quadratic in nature. I can either factor or use the quadratic formula to solve. I believe I'm going to try to factor this. 2 cosine theta and a cosine theta. Now I'm going to make this a minus 1 and this a plus 1 so that I can get it to be a negative 2 cosine theta plus a 1 cosine theta would give me a minus 1 cosine in the middle. And then I have my minus 1 on the end. So that works. Still equal to 0, which means setting each one of these equal to 0 and solving it, cosine theta is equal to negative 1/2, and cosine of theta is equal to a positive 1. Where does it equal negative 1/2? Here and here. This is at 2/3 pi. Running out of room here. I'm going to have to come up here. This one here is when theta is 2/3 pi plus any full cycle later. And then the next one is going to be 4/3 pi plus any full cycle later, 2 pi k. That's this one down here. When does cosine theta equal positive 1? Well, that's only going to happen here. And that is going to happen when theta is equal to 0, 2 pi, 4 pi, right? So how about just a 2 pi k? Yes, you could certainly put 0 plus 2 pi k, okay? Now this is all the solutions. And it looks like that's what they're looking for. They're not specifying a certain interval. So here we go, using a double angle formula. With this number 16 here, it looks like we're going to use another identity. It's going to be probably the power reducing formula because I see that I have just a cosine here, and here I have a sine squared. And so far, we've been solving trig equations that are quadratic in nature, or maybe there was some other kind of manipulation we could do, factoring. Oh, they were quadratic in nature. Or maybe it was just a single trig function and we just had to visualize the unit circle. So if I want to, say, convert these all to cosines, I could change sine squared to, let's see, what could I change? Sine squared right here. Oh, but then I have a 2 theta. Well, it might get a little bit ugly, but one option would be to replace sine squared with I could use power reducing, but actually, why not instead just use Pythagorean identity? That would be probably a better choice. Okay. So I have a plan. 3 cosine theta plus 3 equals 2 times, and instead of sine theta squared, we're going to go 1 minus cosine of theta squared using Pythagorean identity. Okay? Now, a little bit of cleanup. Now that I have it factored and solved, when do I get a cosine value of negative 1/2? Here and here. When theta is 2/3 pi plus 2 pi k, and when theta is 4/3 pi plus any full cycle after that. When does cosine equal -1? When theta is pi plus any full cycle after that. There's my general, or in other words, all of the solutions. Now it's asking for the specifics, right? From 0 to 2 pi. So if it wants the specifics, we're going to say, what do we get when k is 0? We get 2/3 pi. We get 4/3 pi. We get pi. Now, if k is 1, all of these are positive, and we'll add 2 pi to it, which means they will all be too big. If k is negative, take a peek. For this first one here, we would be subtracting 6/3, which would give me a negative 4/3. That's 2 pi, and that's too small. The next one would be giving me a negative 2/3, which would be too small. The next one would be giving me negative pi, which is also too small. So these are the 3 solutions that we would get in this case.